Okay, so calculating delta G for a reaction, the standard change in free energy. And this is the criterion for spontaneity at standard conditions. So there's 3 different methods, and which one you use depends kind of on what sort of information you have. You can calculate the standard enthalpy of reaction and the standard change in entropy for the reaction from heats of formation and standard entropies. And then you can use the equation that relates delta G to delta H and delta S. So that's one method. You can also calculate it directly from free energy of formation values, or you can calculate it from the free energy changes for the steps in a stepwise reaction. Because free energy is a state function. So if we have several different equations or reactions where we know the free energy change, and we can add those up to get a reaction that we want, then we can use that. So the first method, you can calculate the standard change in entropy and standard change in enthalpy from tabulated values. And the form is the same for both of them. That sum of the total change that you're looking for is the sum of the product values. If there are coefficients, you multiply the value by the coefficient. The sum of that minus the same sum for the reactants. And what helps me remember this is, delta is almost always final minus initial. So the products are the final and the reactants are the initial, right? What you're starting with. So then we're going to use this equation. Now, since we're talking about standard conditions, strictly speaking, this only works at 25 degrees Celsius, right? But it gives us a clue, an estimate at other temperatures. So, if we want to do it at some other temperature, we can plug a different value in here for T. And, we have to understand it's not going to be exactly right, but it'll be close. And it certainly might be close enough to be able to tell us whether it's spontaneous or not. Yes?
Up to what range in temperature can we use that?
That's a good question. Up to what range in temperature? The farther from 25, the less accurate. So if you're going, to 1500 degrees, it's probably not going to be so useful. But if you're talking about like normal temperatures that you could achieve in a lab, it's probably good enough. Yeah. Okay, consider the oxidation of NO to NO2. We're supposed to calculate delta G at 25 and determine whether the reaction is spontaneous at this temperature. I didn't think I did. So we need values from the appendix in the back of the book. When I revised slides, I started putting these numbers in there, which is super handy, but this one I don't even have the right chapter number on, so that's not so good. Nitrogen. So, we're using that equation up there, so we're going to calculate delta H and delta S for this equation. We need S0 for NO, for O2, and for NO2. So for NO, S0 is 210.8 joules per Kelvin. For NO2, it's 240.1. And for oxygen, 205.2. So the change in entropy under standard conditions for this reaction is equal to the entropy of the product here, which is 240.1 joules per Kelvin. And the coefficient there is a 1, so I don't need to do anything, minus the sum of the entropies for the reactants. So for no, it's 210.8. It's one of my favorite words. No. Because it's yelling, right? It's all caps. Plus 1/2, I'm going to write 0.5, times the one for oxygen. I'm getting negative 73.3. Thank you. Is that a reasonable number? Yeah, we expect it to be negative, right? Because we're going from, 1.5 moles of gas down to 1 mole of gas. So that should be a decrease in entropy. And then we're going to do the same thing for delta H. I'm going to try writing the delta H's in here. So NO is 91.3, and that's kilojoules per mole. And NO2 is 33.2 kilojoules per mole. And what's the heat of formation for O2? 0. So delta H will be the product, kilojoules per mole, minus the reactants. One of them 0, so just minus the other one. Minus 58.1 kilojoules per mole. I didn't pay attention to it up here. The units in the table are actually joules per mole Kelvin. Because what we're doing here, like when we're multiplying by 0.5, that's 0.5 moles, and that cancels the mole in the denominator. So here, I'm multiplying by the coefficient, which is 1 mole for both of these. So I'm going to end up with just kilojoules. And I don't want to write all those units out, so we're just going to erase that. Does anybody have a problem with that? Everybody okay? Okay, so we've got delta H and we've got delta S. Now we can calculate delta G. Delta G for the reaction is equal to delta H, negative 58.1 56.1. So we need to decide here, are we going for joules or kilojoules? Yeah, what they said. We'll do kilojoules. So that's delta H minus the temperature at 25, it's 298 K, times the delta S, minus 73.3 times 10 to the negative third kilojoules per Kelvin. There's different ways you can do that. Negative 58.1 minus 298 times negative 73.3 times 10 to the minus 3. I'm getting negative 36.3. Kilojoules. Anybody else come up with that? Okay. Is the reaction spontaneous? Yes, because delta G is negative. Any questions? Yes?
Will we be given the values?
You would be given the values, yeah. Nobody knows all of those.
Can you explain the part? Because I thought since both of these were negative, we keep this. So you said the answer is negative? So, okay, never mind, it is fine.
Okay.
Okay.
Any other questions? Rebel?
So, the change from Gibbs to free energy,
Mhm.
like, so Gibbs free energy to the energy of the universe, like, Gibbs?
No. We'll talk more about exactly what that is.
Because I thought since it's negative, that entropy was decreasing, so the reaction should be spontaneous, that's all.
Yeah, so it turns out, as we fumbled through the discussion on Monday night, that you have to, it's the combination of change in entropy and change in enthalpy and the temperature, because entropy is temperature dependent. It's the combination of those, which is gives free energy, that tells us whether it's spontaneous or not. We can have a negative delta S and still have a spontaneous reaction. We can have a positive delta S and have a non-spontaneous reaction. It just depends on some other things. So usually, if you didn't have any more information, if entropy was decreasing, you'd say, well, it's probably not spontaneous. But here we have way too much information. Anybody else? So this one is estimating standard free energy change at a temperature other than 25 degrees Celsius. So let's see if I can do this. Yeah. I need some of these numbers. Write them on the board. Minus 73.3. Joules per Kelvin. And minus 58.1. Kilojoules. Period. And our delta G was minus 36. At 25. There's no point in calculating all these things over again, right? So here we're supposed to calculate delta G at a temperature of negative 55. So we need to turn that into kelvins. So negative 55 plus 273. 218 Kelvin. Oh, yeah, look at that. I wrote it down. That's okay. So at this new temperature, if I'd actually read my own slide, I would have seen that. We've got minus 58.1 kilojoules minus the new temperature, which is 218 Kelvin, times the change in entropy. I'm getting minus 42.1 kilojoules. Anybody else get that? I cheated. I went up to the previous equation in my calculator and changed the 9 to a 1 and hit enter. Ta-da! Okay, so at 25 degrees, it was minus 36. At negative 55, it's negative 42. Is it more spontaneous at the lower temperature? Yes. The more negative it is, the more spontaneous it is. As it gets closer to 0, it's less spontaneous. It goes past 0, now it's non-spontaneous. So more spontaneous at low temperatures. And it doesn't take too much imagination to see that being able to predict things like this would be really useful for engineers, especially chemical engineers, where, they're trying to do this whole big process, right, and do it efficiently. And so, one of the things that you can control is temperature. And so maybe it'll work if it's better if it's colder. Mm-hmm.
Can you go back 2 slides to the first one you did?
I can go back there,
I don't think I copied it down.
but I can't.
Your work's gone?
Yeah. I can get it, but it's not an easy process.
It's okay.
It involves looking at the video and taking a screenshot. There's probably a better way, but I haven't figured it out yet. Okay, so we can calculate delta G from free energy formation. So the free energy of formation is a change in free energy when 1 mole of a compound in its standard state forms from its constituent elements in their standard states. Free energy of formation of pure elements in their standard states is 0. So delta G behaves a lot like delta H. They have the same sign conventions, and elements in their standard states are 0. So again, we're going to take the products, multiply by their coefficients, and subtract the reactants. See here, I was smart. I put the table in there. One of the reactions that occurs within a catalytic converter in the exhaust pipe of a car is the simultaneous oxidation of carbon monoxide and reduction of NO, both of which are harmful pollutants. Use standard free energies of formation to determine delta G for this reaction at 25 degrees C is the reaction spontaneous at standard conditions. So here we have a table of delta G values. So we can, just pull these out and use them. So delta G standard for the reaction will be the products. So we've got 2 moles of CO2. We've got 2 times CO2, which is negative 394 kilojoules. I'm kind of cheating with the mole units. Plus N2, which is 0. So those are the products. And we're subtracting the sum of the reactants. 2 times carbon monoxide plus, plus 2 times, 87.6 kilojoules. And the pluses here are just to point out, we didn't just forget the minus sign, it is actually positive. So 2 times negative 394 minus the quantity, 2 times negative 137.2 plus 2 times 87.6, getting minus 688.8. Is that reaction spontaneous, standard conditions? Oh yeah. That's a very negative delta G. Any questions? So the third method is stepwise reaction. Free energy is a state function, so we can use Hess's law that says if we record the delta G's, or we know the delta G's for a series of reactions that stepwise add up to the reaction we're looking for, we can figure out delta G for the reaction from those. So the same relationships go for free energy as went for enthalpy. Remember, we learned some different rules when we were looking at equilibrium constants, but these are the same as for delta H. So if you multiply the chemical reaction, the chemical equation by a factor, you multiply delta G by the factor. If you reverse the equation, you change the sign. And we can add up the individual pieces. So this is different than equilibrium constant. Equilibrium constant is like on steroids or something, right? You reverse it, you don't just change the sign, you invert it, right? If you multiply by a factor, you don't multiply K by the factor. You raise it to the power, right? And instead of adding them together, you multiply them together. So it's just like extreme, right?
So this is, like it says, just like Hess's law.
This is just like delta H, just like Hess's law, what we did in 1A. Okay? Okay. Find delta G for this reaction. I was just teaching my 1A students how to do this. So the nice thing about the problems in a class is they give you the equations that you need and nothing else, right? If you're trying to do this in real life, you're going to go look in the CRC, which has pages and pages and pages and pages, and you're trying to figure out what things you can combine to get what you want. Very tedious. Okay, so how do we put these together? There's different approaches. What seems to work pretty well is let's identify what these things are. I can't write up there. No, that's not what I wanted to do. This is what I wanted. There we go, highlight. So N2O is a reactant, and let's find it in these other reactions. And we've got NO2, and NO2 is here and nowhere else. And then we've got no. Yeah, it's just a thing I do to amuse myself. And that shows up in two different places. So putting these together can end up being a bit messy. So I kind of like to start in the same place every time, just so I don't get lost. So I'm looking for an equation that has this reactant, and I want to write it in the direction where this is a reactant on the reactant side, right? So that's going to be this one down here. It's already in the correct order, so we're good. So we're going to have 2 N2O gas going to 2 N2 gas plus O2 gas. And we didn't do anything to the equation, so delta G is the same, minus 207.4 kilojoules. Now I'm going to look for NO2. So we have NO2 showing up in one place. It's a product. So I'm going to take this reaction and reverse the direction. So I'm going to do NO2 gas. It's two of them. 2 NO2s to make 2 NOs and oxygen. Stupid group text. So how do I change delta G? I changed the sign because I wrote it backwards, right? So I'm going to change the sign from negative to positive. And then I want to end up with no on the product side. I've already got no on the product side. Over here, let's go ahead and identify these other guys while we're at it. But the thing is, I need these oxygens to go away. So I need that third equation. So it is written in the correct direction. So N2 gas plus O2 gas. It's helpful to keep your arrows lined up. Going to 2NO gas. Just remind ourselves of what's going on. And so what is delta G for that one? Yeah, it's 175.2 because we didn't change anything. Okay, so we got all of the reactants and products on the correct sides. But we're going to have to do some multiplying or dividing or something because they're not adding up right. If I add these three equations together, I'm going to end up with 4 no's and I only want 3, right? I'm going to end up with 2 of these and 2 of those, and I only want 1 of each of those. So we could multiply things so that the O's and the N's cancel out, or we can selectively divide things. We'll end up dividing at the end if we do it the other way. So I'm just going to do it in the shortest number of steps. So I've got 2 oxygens over here and 2 nitrogens. And this is twice as big as it needs to be, and that's twice as big as it needs to be. So how about we'll divide both of these by 2 so that the coefficients on these guys are correct. So this is times 0.5. That's the same as dividing by 2. And times 0.5. So now what I have is half of an oxygen and half of an oxygen, and I get rid of the 2's. Does that make sense? You okay with that? Okay, so now if I add 1 no and 2 no, I get 3 no's, and these guys are going to be 1's. So that's encouraging. So let's go ahead and add these together. So I have 1 mole of nitrogen on the left side, and I have 1 mole, where'd it go? 1 mole on the right side. So those are going to cancel out. I have a combined 1 mole of oxygen and 1 mole of oxygen, so those are going to cancel out. So I'm going to end up with N2O gas plus NO2 gas, making 3NO gas. So then I need to add these up also. So 0.5 times negative 207.4 plus 0.5 times 71.2 plus 171, 5.2, 107.1. I think overall the concept is pretty straightforward. Doing it can get a little messy. Any questions? Is this reaction spontaneous? No.
I remember back in 1A where the oxygen wasn't O2, it was like O1 or something like that. Does that do with what we're doing here? Or I don't know.
You mean like in a hydrate
I believe so, something
with
like that.
half? Yeah, they use a coefficient of 1/2 in hydrates because otherwise you have to multiply all the ions by 2.
Okay.
So it's just sort of a convenience thing. And it's like, well, how can you have half of an oxygen molecule? Well, you can't, but you can have half a mole of oxygen molecules, right? So these equations here do not work on a molecular level, but when are we doing that? Almost never. Any other questions? Okay. Why is free energy free? What exactly is free energy? So we like to use the chemical energy released by a chemical reaction to do work. An example is the combustion of gasoline used to move the car, right? The change in free energy represents the maximum amount of energy available or free to do the work. So lots of times the change in free energy is less than the change in the enthalpy. Where does the extra energy go? Heat tax. It's lost to heat. So here is the maximum work available. Here we have the energy given off by the reaction. I'm sorry, this is the maximum work that can be done. And this is the minimum heat lost to surroundings. So this would be the delta G. So the Gibbs free energy isn't like energy that you get for free. It's energy that is free to be used for constructive purposes. Does that make sense? So change in free energy represents a theoretical limit as to how much work can be done by the reaction. In a real reaction, the amount of energy to do work is always less than delta G because you lose some to the surroundings as heat. Only reversible reactions can approach the theoretical limit because a reversible reaction occurs infinitesimally slow. So the free energy gets drawn out in little teeny tiny pieces that exactly match the amount of energy produced by the reaction. So in theory, that could happen, right? But it would take forever. So the free energy is the limit. And, in practical circumstances, you'll never get to the limit. So here's an example of a reversible process. A reversible process is one where you can change the direction of the reaction by making a teeny tiny change. So here we have some sand on this movable platform which is being supported by a gas underneath, right? The sand has pushed the platform down, and if we take away one piece of sand, the platform goes up a teeny bit, right? We take another one away, it goes up a teeny bit. So we can incrementally remove the sand, and the gas will expand. You can go the other direction as well by adding a piece of sand. Little teeny. This is like in calculus where you've got the area under the curve and you're chopping it up into these little teeny tiny pieces, right? So all real relaxation. All real reactions are irreversible. They do not achieve the theoretical limit. When you draw current from a battery to do work, some energy is lost as heat due to resistance in the wire. And the amount of energy needed to charge the battery is more than the amount of work done by the battery. So this makes the whole idea of renewable resources and green energy and electric cars and stuff a lot more complicated. Because it's great to say, I've got an electric car, I'm not polluting the atmosphere, right? I'm not contributing to the greenhouse gases. Well, when you're driving your car, you're not. But how are you charging your battery? Where is the energy for that coming from? And that's not even talking about making the battery and what you do with the battery when it's done being useful, right? It gets very, very complicated. Anybody have any questions about that? Yes.
But taking the energy from to charge it, that's better than gasoline pollution, or
Well, it depends on where the energy to charge it comes from. If it comes from a fossil fuel burning power plant,
do you know what they use at the charging stations?
well, they're getting electricity from the grid.
Okay.
So it's whatever PG&E is using to provide the power. Now, they do have, some windmills and they use hydroelectric stuff, but there are also coal-burning power plants. And so if your energy is coming from burning of petroleum products, then you're probably actually burning more petroleum products because of the heat lost in the transmission and charging the battery and running the battery than if you were just burning the petroleum products in your car. So it's a very big, complex problem. Now, if you've got solar panels on your house and you're generating enough energy there that you're actually feeding the grid and not taking from the grid, well, now you're in a better place. But there's still some what ifs. Yeah. So in a real cyclical process, like a battery discharging and charging, the system may return to its original state, but the surroundings don't. So there's a permanent dispersal of energy into the surroundings. For a chemical reaction with a positive delta G, non-spontaneous, that delta G represents the minimum amount of energy required to make the reaction occur, as opposed to the spontaneous process where that's the maximum amount of energy that could be used to do work. This is the minimum amount needed to cause this non-spontaneous process to work, and it's probably going to require more.